He abandoned that world in 1988 to go to academia at the Oregon Graduate Center, where he worked on analysis and optimization for parallel execution of programs. And while he was there in Oregon, he did a very academic thing and wrote a textbook entitled High Performance Compilers for Parallel Computing. Now, deciding then that academia could be in his past, he moved in 1996 to the Portland Group Incorporated, where he initially worked on high-performance Fortran. And then some years passed, and he came to SC17, where he attended the very first CUDA tutorial, and he told me that afterwards he thought, there has to be a better way. So that thought in mind, with support from NVIDIA, he developed the PGI Accelerator Directive Programming Model, and that in turn led to a joint venture with NVIDIA, Cray, and Oak Ridge to develop the Open ACC specification. In 2013, NVIDIA acquired the Portland Group, and he has continued working there now on heterogeneous compilers. And in addition, he is the chair of the Open ACC Language Committee, which just this month ratified a new standard. So I will turn the floor over to him in just a second, but one thing I wanted to let you know is that at the end of this talk, I hope that you'll be happy to get up and ask questions at the microphones that are there in the aisles. But if you would like instead, if you go to the electronic schedule for the conference and go to this event, you'll see a link where you can enter questions and you can vote on questions that other people enter. And I'll keep a little eye on those in case somebody's shy about getting up and asking the questions. We can take them from there. So, Michael?
Great. I want to start by thanking whoever nominated this paper for the Test of Time Award, and for the committee, to thank the committee for considering and then eventually selecting that paper for the award. That's quite an honor. And thank all of you for showing up. During this talk, I'm going to answer 7 or 8 questions. First is, what is iteration space tiling, and why was this paper more iteration space tiling? I'm going to assume, without fear of much contradiction, that most of you know what iteration space tiling is, or at least you have some clue. But I'm going to go over it anyway. I'm going to give my 30-minute talk in 2 minutes. So if we look at loop vectorization, you have a long loop, and you have vector operations. The old Cray machine, the vector operations were 64 long. On SIMD processors today, AVX would be 4 long for double precision, or 8 long for AVX 512. So what the compiler does is split that loop into 2 loops. There's an outer strip loop and then an inner element loop. And the element loop turns into those vector or SIMD instructions. So the element loop actually goes away. The outer strip loop steps in chunks of 64, 8, or whatever it happens to be. Now, if the trip count doesn't exactly divide by whatever your vector length is, then there's going to be some cleanup code either at the beginning, it'll run a short vector, or you have to do some cleanup code at the end to run a short vector. Or if you're on a SIMD machine, well, then alignment is a consideration. So maybe you do a little short operation at the front to align one of the arrays, then do your SIMD operations, and you may have to do some cleanup code at the end as well. More detail than you wanted to know. Well, what if you had a multi-dimensional iteration space, say a 2-dimensional iteration space? So you take the nested loops. Each loop, you'd break it into 2 loops, an outer strip loop and an inner element loop, and then the inner loop is an outer strip loop and an inner element loop. And you take the strip loops and move them outwards, and the element loops and move them inwards. Well, that's a 2-dimensional analog of strip mining. That's basically tiling. So if we take the crossbar or the T up here, I'm going to say, let's assume that every iteration, every pixel on that orange blob across the T there is an iteration. And suppose there's 320 iterations across and 64 iterations down. That's my 2-dimensional iteration space. And I'm going to tile this to 16 by 16 tiles. So I get 20 tiles across and 4 tiles down. So I have a 4 by 20 block of tiles. Now, tiling in compilers was initially designed to optimize for cache hierarchies. Caches, you have to remember when this was done, 1989, set your clock back. Caches were small, 8K, 16K. No one ever heard of an L2 cache at that time. So the point was to optimize the code in the tile so the working set of your data would fit into the cache as much as possible. So those tiles would be relatively small. And the generated code would traverse all the iterations within a tile, then move to the next tile and do all those iterations and move to the next tile and so on. Now, the compiler could order the tile loops to step across tiles in either direction, and it could do that based on things like locality between tiles, so that you've already warmed up the cache for one tile, maybe you can reuse some of that data in the next tile. You can also order the loops within a tile to do, say, vector operations in one direction or the other, or register locality or what have you. Now, what about parallelism? So this was the actual topic of this paper 20x years ago. So if there's parallelism, we can use the tile as the unit of scheduling and synchronization. It reduces the scheduling and synchronization overhead because it's only once per tile, not once per loop iteration or once per row or what have you. So here, again, take the crossbar or the T. If there are no dependencies, then I don't need any synchronization, but I do need scheduling. If there's no dependencies, you could do it. The iterations assign each of 4 processors to a row of tiles, and each processor could do the execution of each tile, taking advantage of locality within the tile, and move on to the next tile, and so on. In 1989, 4 processors was a good number. Or you could do, if you had more processors, you might schedule it the other way, or you might do some other chaotic or other scheduling optimization. But what if you had dependencies? Say you have dependencies going down. So in this example, I'm assuming the origin that is on the top left, and inner loop goes across, and the outer loop went down. What if your dependencies went down the outer loop? Well, then you'd probably want to schedule the tiles so the same processor did tiles in the same column, so you don't need to synchronize between processors. That would be a scheduling optimization there. And if the dependencies went across, then you would want to schedule it so that the same processor did the tiles in the same row. What if you have dependencies in both directions? Well, then you might do something like the crossbar of the N. It's the same number of iterations and the same number of tiles, but now I've got time flowing down. In the first time step, I have one processor doing a tile. It does all its work, and then it synchronizes, and then I have 2 processors doing 2 tiles, and then they synchronize, and I have 3 processors doing 3 tiles, and so forth. Now, you can obviously see that I'm limiting the amount of parallelism. I can only get 4 processors busy in this case, whereas I had 64 iterations. Theoretically, I could scale this up to where I had 64 processors being busy if my tile were 1 by 1, or if I didn't do tiling. But it's a trade-off, trading off the overhead for scheduling and synchronization against the amount of parallelism. And again, set your clock back. There wasn't a lot of parallelism in most processors in those days. So the goals were you have atomic tile execution. The tile executes completely without any synchronization or communication between any other processor. And I'm going to be saying processor because in 1989 the word core had not been invented unless you were talking about apples or the planet. Parallelism between tiles, vector operations within a tile, locality within a tile, and, if possible, locality between tiles as well. And the process was take my iteration space and maybe reshape this a little bit, and then tile the loops in that iteration, in the reshaped iteration space, and then maybe reshape the tile loops and order the tile loops and do your scheduling between tiles, and order the element loops and do your scheduling within the elements. So now we have a separation of concerns. I can optimize within a tile completely independently for optimizing between tiles. Separation of concerns, there were a number of us, not a large number because it wasn't a big workshop, 3 weeks ago at a Dogstool seminar, and the term separation of concerns came up a heck of a lot. It was a drinking game by the time we finished. And then the other optimization elements were selecting the tile size and shape. And here I'm showing rectangular, in fact, square tiles. They don't need to be square. They don't even need to be rectangular, but the ones I show will all be exactly this shape. So that's pretty much it. There's a 30-minute presentation in just a couple of minutes here. And no performance results. I didn't have a parallel computer I could run performance on. I didn't even have a compiler I could run performance on at that point. I was at OGI, or OGC, Oregon Graduate Center, more or less working by myself. But I guess the bar to get a paper into supercomputing in those days was significantly lower. So you might ask, question 2, why is this paper worthy of a Test of Time award? I wondered that myself. So as was said, this Test of Time award is given to an outstanding paper that has deeply influenced the HPC discipline, has changed HPC trends, and I'll argue later on this has in at least one minor way, which I'll get to. And it's an incentive for researchers to send their best work to supercomputing. So my best work was 30 years ago. It's been downhill ever since. And understand how results last in the HPC discipline. So what makes this worthy? Well, if you go to the ACM Digital Library and you search for the title, More Iteration Space Tiling, you get to the page for this particular article. Don't need that. And then you click on the Publication tab, and which it gets you to is a tab where you see a link to the Supercomputing 89 proceedings. But further down in that tab, you see a link to the conference series, the International Conference for High Performance Computing, Networking, Storage, and Analysis. I swear that title gets longer every couple of years. If you click to that page, you taking notes? Click to that page, you'll see at the bottom of that page the 10 most downloaded articles in the last 6 weeks. But there's another tab. Click on that tab to see the 10 most cited articles in the history of the Supercomputing Conference. And this paper was number 9 on that list. So I don't know what counts as a citation. I think the citation count in there that they show there is 144. If you go look at Google Scholar, there's a much different number, a much larger number, but that's the number that puts me in the top 10, so that's the number I'm going to go with. I also note that the list of citations that are given there include none of them written by me. I'm sure I cited my own paper somewhere, so I don't think it's a complete list of citations. I'll also note that the other 9 papers in the top 10 are all newer than this. Some of them significantly newer. They are not eligible for the Test of Time award yet. So they not only have more citations, they got them faster. Their citation velocity is significantly higher. But in the past 28 years, this paper has had at least one citation every year, including this year. So that says something about its lasting legacy anyway. We'll come back to that topic a little bit later. So was this paper the first to actually tile loops? No. So most of us have or should have heard by now of block formulations of algorithms, block matrix multiply, block LU decomposition. These are all well known. You still see publications about these. They're all intended to optimize for cache or for memory hierarchy locality or to optimize communication between separate processors. Back in the 1960s, before virtual memory, before even I was doing computing, there were out-of-core algorithms. For all you young folk, core meant the actual physical magnetic donuts, the cores that were used for memory. So we had out-of-core algorithms where the program, under program control, paged in blocks of data from disk. Disk is like an SSD, but it spins. So you page in blocks of data from disk, and then would do some processing and page the data out under program control. So these are out-of-core algorithms because there was no virtual memory. If the data didn't fit in the memory, you had to do something yourself. That was essentially tiling of the algorithm, but done under heroic program control. In the 1970s, we had the first version of BLAS, the basic linear algebra subroutines, basically vector operations. Shortly after that, there was BLAS2, matrix vector operations, and then BLAS3, matrix-matrix operations. Well, the BLAS3 routines could be written in terms of BLAS2, and the BLAS2 routines could be written in terms of BLAS1. So why do you need a BLAS2 and a BLAS3? Well, you don't need them unless there's something you can do that you can't do if you cast it in terms of the lower level. And that was optimizing for different levels of your memory hierarchy. So BLAS2 in particular, you could take advantage of vector register locality that you couldn't if you wrote it in terms of vector operations. In BLAS3, you could take that triply nested loop and tile the loop manually, but tile the loop to optimize for memory hierarchy locality. So all these things were quite well known. Had been done manually for years, if not decades, before this paper was written. So there's no way I could say I invented loop tiling. So let me change subjects. Where did this work arise? So as Liz mentioned in the introduction, I was a graduate student at the University of Illinois. So I'm going to go backwards, and I'm going to get to the graduate student part. All this work was published while I was attempting to build an ultimately unsuccessful career in academia at the Oregon Graduate Center, which was soon renamed the Oregon Graduate Institute, because an institute is better than a center. And it was eventually merged with or acquired by, I'm not sure which, the Oregon Health Sciences University. And then all the faculty were moved to OHSU facilities. The building where I sat is now a hole in the ground. No legacy there. This work actually started when I was at Cook & Associates, KAI. KAI was acquired by Intel. It happened to be acquired by Intel the same year that OGI was merged with OHSU. We'll come back to that. But this work at KAI was an outgrowth of the restructuring compiler work at the University of Illinois. This was David Cook's research project, the Paraphrase project, which has had a couple of incarnations, but this was the first one. I say restructuring compiler, so this is reordering the operations, in particularly reordering the loops. Interchanging loops was a big deal in those days. It was a huge deal. And it really, once you start being able to do things like automatically reorder the loops, like take that T crossbar and turn it into an I, well, it changes the sorts of things that you can start to think about doing automatically. Loop interchanging, loop reversal, loop skewing. So loop skewing is turning the T crossbar to the N crossbar. Loop parallelization, vectorization, and so on. So we did these transformations with three things in mind. One of them, legality, profitability, and code generation. And we weren't the first to consider these, but we were the first, or one of the first, to separate the legality test from the transformation and the profitability test. The legality test was essentially dependence analysis and studying the dependencies to see whether whether the optimization would preserve all the dependencies that you had. I'm going to have an aside here. Graduate student, Dr. Utpal Banerjee was a graduate student at Illinois when I was there. He was the inventor of Banerjee's inequalities. It was the first actual mathematical approach to the general array dependence problem. It was not the last. He had several more after that. He passed away recently, so as the first of my generation of grad students to leave the planet, I'm very sorry to hear that. Anyway, all this work was really related to a lot of previous work on systolic arrays and uniform recurrence equations, which dates back to at least 1968. At least there was a paper in 1968 that has a lot of citations. Luckily, it was not at SC, or it would have more than mine. That work restricted the form of the programs to make the compiler analysis easy. So they didn't need this fancy dependence analysis that we had been working on at Illinois. And they took the iteration space and applied linear affine transformations to turn the loops into an outer time loop and an inner space loop to determine what operation, where an operation was an iteration of the loop, what operation was done at what time step on what processor. And they would schedule the communication between the processors. And if you look at some of the old systolic array articles, they had systolic arrays that were squares or two-dimensional systems or three-dimensional systems, and data pumps in from one side and pumps in the other side, and all scheduled to arrive at the right place at the right time and do some operations. And so it's mostly for signal processing. So it's a limited application domain, but an important one. Important enough to get a lot of publications at the time. So the loop transformations we were looking at were essentially, again, mostly linear affine transformations. Loop interchange is basically transposing the iteration space. Loop reversal is flipping it around one of the major axes. Loop skewing is what we saw at the T to the N crossbar, so that's offsetting the rows by the column index or vice versa. And we knew that. We even talked about that a little bit. We never made the critical next step. The next step would have been, and other people did make the step, people brighter than we were, the next step would be to say, I don't need to consider these as loop interchange followed by skewing. This is a linear transformation, that's a linear transformation. Let's compose the transformation and then think of it as a single optimization that's the composition of two other optimizations. We never made that critical leap, so the research community left us in the dust on that. So we had this toolbox of loop restructuring transformations. One of the goals of this toolbox was to automate everything you can do by hand. In particular, Jack up here in the front row. Everything he can do by hand, we wanted to automate. Now, we're not as smart as Jack, and our compiler is certainly not as smart as Jack, but a compiler is more tireless than all the Jacks of the world. So if you can teach a compiler to do something, then you can do that on every program, not just the innermost loops, not just where you think it applies, you can do it everywhere. In particular, Joe or Sally or whoever else or Liz can take advantage of this optimization because the compiler would do this automatically. So that was our goal. For an example, I saw an article about the 6 ways to do a Cholesky decomposition. So a Cholesky decomposition is basically, it's like an LU decomposition of an array, but it's for a symmetric positive definite matrix. So it's symmetric, so you're going to decompose it into L and L transpose. So since they're the same, you only need to do half the work. You just compute L. And the classical Cholesky decomposition, you have 3 loops. You have an outer loop, but they're not tightly nested. You have an outer loop, and then there's one statement in here that does a square root on the diagonal. And then a second loop, and there's another statement in here that does the divide of the column by the diagonal. There's a third loop that then does the rank 1 update of the rest of the columns from this column that you just did the divide into. Well, that's your classical IJK order, but you actually can restructure that in any order. The problems are, well, the loops are not tightly nested, and they're triangular. So they're not rectangular. So in order to automatically compute the different orderings, your compiler or tool has to know, how do you take a triangular loop and build the bounds? You're going, let's see, this way, and I'm going to transpose it this way. So here it went from 1 to I, now it's going from I to N. You have to modify the bounds. And you have these statements, and depending on how you reorder the loops, the dependencies sometimes mean the statement has to come after the inner loop instead of before the inner loop. Well, we eventually figured that out, how to automatically generate, detect for legality of the 6 methods of Cholesky decomposition and how to generate the code. We didn't think about profitability at that point, and I'll have to admit I haven't yet. But we're very proud of that. It was great work. So that's the framework that this paper was written in. So the next question would be, was this the first work to do something like tiling to optimize for memory hierarchies? No. So going back to Illinois, we had another graduate student, was Abu Sufa, now Professor Walid Abu Sufa, who was working on loop optimizations to improve virtual memory performance. Now, his work was done 10 years before this work, so it was in the late 1970s. And at that point, the memory size on a system was about the size of a cache today. So you can imagine it would apply pretty well. So if memories were small, you have large data sets, you need to page data in and out, and you want to minimize the amount of data traffic to and from that spinning disk because that's really, really slow. So he was saying, let's block the loops and automatically generate the blocked version. And it worked really well. He had another idea as well to change the data layout of the matrices so that a block of the matrix, the data that would be accessed by a block of the loops, is all contiguous in memory. Rather than laying it out row-wise or column-wise, lay it out block-wise. So the iteration space tiling idea was based entirely on his work, and it cites that throughout, although we never considered data layout optimizations, and we still don't. Well, okay, was this the first work to do tiling for parallelism? No. There was a paper just the previous year from some researchers in France, François Uruguay and René Triolet, called Supernode Partitioning. It was in the Principles of Programming Language conference. Their idea was somewhat similar, but they used a different transformation. They took the iteration space, now it was some number of dimensions, any number of dimensions, and they would take hyperplanes through the iteration space. So they're working in the iteration space dimension rather than the program dimension, and partition this so they could have irregularly shaped supernodes. So for them, a node was an iteration and a supernode was a blob of iterations. In fact, they really came from the systolic array community, and so what their notion of a parallel program was an outer loop that executes sequentially, that's your time loop, and the inner parallel loop that executes all at once, and so that's kind of your space loop. So it came from that community. So now you might well ask, so what was new in this paper? How did it even get accepted? Okay, so we're using this, doing this tiling with loop transformations instead of some abstract representation of the iteration space. It's very straightforward to do tiling. We separated the optimization within a tile for vectors or SIMD execution or register locality, and then between tiles for multiprocessor parallelism and synchronization and cache locality between tiles. And as I said before, separation of concerns is generally a good thing. So I think I'm up to question 6. What's been done with iteration tiling since then? It's been 28 years. It's got a lot of citations, I claim, without proof. Well, there's been a lot of work on things like finding tile sizes or scheduling the tiles, taking data alignment into account, adding loop fusion to the mix, tiling for register locality, tiling for non-shared memory. Lots of work on tiling as iteration space partitions. So going back to the supernode partitioning style of analysis where you're looking at the iteration space and you're splitting it up abstractly and then generating code from that. In fact, unifying the linear, affine, and unimodular transformation framework, well, this all turned into the polyhedral optimization framework. And tiling is a decidedly non-linear optimization, but they were able to fit this into that framework. It's really, the polyhedral framework is really kind of the culmination of all the loop optimizations that had been done when I was young, put into a single framework by a lot of guys that knew a lot more and know a lot more than I ever did or ever will. It's a great piece of work, and I'm quite impressed with what they've been able to do. Other things about tiles. You look at OpenMPs, does static scheduling of loops. Well, it's more or less blocking the loops. It makes it look an awful lot like a tile, although if you only have one loop, it's more or less a one-dimensional tile. If you program a GPU with CUDA or OpenCL, you have a grid of thread blocks. The thread blocks have a multi-dimensional shape of threads within a block. That's more or less a tile of operations going on. It's an implicit tiling of the space of operations that you're working on. OpenACC, we mentioned we just have a new version, but it has a tile clause for scheduling 2 or higher dimensional manually created tiles of iterations for tightly nested loops. So there's a lot of citations of this paper, but I think there's probably not a lot of direct use of the ideas, the method that came from the paper. And obviously I had no artifact, so nobody could do anything with my particular transformation here. So what was the critical contribution of this paper? What was the thing that influenced HPC? Well, you might sense my ambivalence about accepting this award. So the question 7 will be, why did I accept this award? So I'm going to digress. There's an organization called the Consortium of Computing Sciences in Colleges. This is mostly smaller, largely private colleges. Nationwide, they have small regional conferences where they meet together and they talk about things like curriculum. These are non-research colleges. They're talking about computer science curriculum, textbooks, what works, what doesn't work, new technology that's coming up, what you should be teaching and what you're not teaching, and so on. In 2010, the host institution was George Fox College, or George Fox University, which is a small private school in Newberg, Oregon, about half an hour from where I live. The organizer was Professor David Hansen. David Hansen was a PhD graduate from the Oregon Graduate Institute. While I was there, he'd taken a class or two from me, and he knew I was interested in parallelism. He had come to some of my seminars, so he thought, 2010, parallelism is hot, let's invite Dr. Wolfe to give us a keynote talk about parallelism. Well, I was wondering what this group was. Is this a real conference? Is this really worth my time, my precious, precious time? So I looked up their website and looked up some of the other conferences they had on previous years and to see who else had given keynote talks there. Well, Barbara Simons, ACM past president. Larry Wall of Perl fame. Bjarne Strostrup, inventor of C++. How can I turn down an invitation to join that list? So somewhere there's a list of these names, and in the middle there is my name. They won't know who I am, but I'm on that list. So I was notified about this award. I asked someone where I work whether this was appropriate for me, and his advice was, take the award, put it on your CV. Well, a CV is valuable when you're looking for a job, but I'm at the other end of my career. My next job will be amateur gardener. But then I looked at the other names on the list of awardees. David Bailey, Horst Simon, Jack Dungera, others more to come. How can I not want to be on that list? So years from now, no one will remember me, but my name will be there. This will be great. So the penultimate question, the penultimate question is, what was the critical, lasting, the real impact of this paper in the HPC community? It didn't invent loop blocking or iteration space tiling. That had been done for decades manually. It wasn't the first use of tiling in a compiler. It wasn't the first use of tiling for parallelism. It didn't use the tiling method that's most used today, but it did popularize the word tiling. Without this paper, we wouldn't be calling it tiling. And tiling is used everywhere. At this workshop in the Dogstill Castle a few weeks ago, at least a third of the articles, or a third of the presentations, talked about tiling in some sense. Earlier this week, someone was at, I think, the LLVM for HPC workshop. He said every article, every presentation had something about tiling. He never thought about it before, but now he's sensitized to the word tiling because of this award. So tiling is everywhere. So where did that name come from? So some of you may have heard this story. I gave a tutorial yesterday. I was talking all day. You have to excuse the voice here. So where did that name come from? Well, the name that Abu Sufa used was blocking, loop blocking. We're talking about high-performance computing. We don't want loops to block. We want them to run, right? Blocking, that's a barrier. We want them to execute. We want them to go as fast as possible. So loop blocking is a bad word. Says, well, what else can we use? Chunking. Block mining. The list gets thin really fast. So Professor Paul Woodward, who was at Minnesota, he does these very detailed optimizations for memory locality, and he generates these optimizations for bricks of data. So the brick is the data subset that's used inside inside a chunk of, inside what I would call a tile. So we didn't think of bricks, but bricking, loop bricking. No, that wouldn't have worked either. So I was agonizing about this. Groups, parts, things, I don't know what. So I have a very strong recollection. This was in about 1986 or 87 when we were working on this at KAI at the time. I was in the kitchen, in the dining room, late at night, children were in bed, with a thesaurus in front of me, block, chunk, strip, part, group, trying to find any word that's appropriate. And my wife asked, so what are you doing? And I have these pictures of square things and blocks chunked up, try to motivate the mind. So I explained to her what I was trying to get to. Well, my wife was a ceramic engineer. She says, what about tile? And my knee-jerk response, because I'm a jerk, is tile. That's a horrible word. That'll never work. Tile. Tiling. Loop tiling. iteration space tiling. That's pretty good. And the story was written. So, it still brings up the question, what was my critical contribution? It wasn't even the name. So my contribution was obviously marrying the right woman. So once again, I want to thank the committee for selecting this paper for this award. I want to thank all of you for staying to the bitter end, and I want to thank my wife for making it possible. And I guess we'll take questions at either any of the microphones if any of you have an axe to pick.
It was a really interesting talk to me because the date of this paper was just before I got my own start in parallel computing, and I thought about things like tiling iteration spaces. And I have seen there are quite a number of young people here in the audience, and I think it would be fun to hear from some of you with questions about your how this talk fits into your world. But as we wait for people to kind of think about questions, for a while, we only had one question that was submitted online, and I think you might like it. Does Michael Wolfe not believe in PowerPoint presentations? I think it came from a fan of bullet points. So
we can't talk about bullets anymore. It's politically incorrect. Let me take a shot at that answer. I was giving a talk, not a slideshow.
I see a question asker there.
I wonder if perhaps what you have shown is the importance, in order to make a really lasting impression over time. I think this is what you've said, is just choose the right name for things.
Choosing a name is important. Having a good name is really a good idea. So this was an example of that. And so agonizing over, when you have something new, agonizing over getting a good name is time well spent. Top 500, that's a good name.
It is. Okay, so Michael, do you see loop tiling still heavily used in today's applications, particularly large-scale applications?
So the question is, do we see loop tiling in use? Certainly. I mean, that's a delaying technique. Repeat the question, right? So certainly you see it in use. When, for instance, today we have OpenACC compilers. We're generating code for GPUs, and we will generate tiled versions, so where the inner loops will get tiled into non-linear, rectangular blocks to take advantage of data locality in both directions, both dimensions within a GPU thread block. It's more detailed than you want to know, but yes, we do it. Other people do it. Data locality is very important. It has been, will continue to be. So you see it. You still see articles about blocked versions of matrix multiply and LU decomposition. I saw one earlier this year.
And related to that question, which large C++ compilers implement loop tiling?
Which large compiler? Are there any small C++ compilers? That's kind of an oxymoron, is it not? So analyzing the analysis you need to do loop tiling does not fit very well with C and C++, does not fit well with C or C++ where you only have vectors. You don't have multidimensional data objects. And you might say, well, I'll just linearize my array. That's a matrix, linearized, but it's really a matrix. Yeah, but the compiler doesn't see that. It sees the vector. And so it's really hard to do that sort of analysis. So for C++, I'm not saying it's impossible. I'm saying it's very difficult. And yeah, so it's really difficult. I don't know that will proceed. I have heard, just here, that there's some work on trying to add real multidimensional arrays to C++, which I think is the most important feature for HPC to make it a truly viable replacement, if you want, for Fortran. That's my opinion.
And the second half of that question asked about which spec benchmarks were auto-tiled.
Which spec benchmarks were auto-tiled? Well, MGrid. You want more than that? I don't have them memorized, sorry.
Yeah. Okay, let me double check to see if we have more questions. Yeah. Is dynamic runtime scheduling of tiled loops possible?
Yes, we have a question back here now.
Yeah.
Yeah, Carlos Malstein, UC Santa Cruz. So it occurs to me that you said earlier that you didn't actually ever look at data layout.
We did not look at changing the data layout, no.
Yeah, so one of the things that I wanted to get to is like in storage systems, especially large parallel storage systems, you have a lot of data partitioning. And it occurs to me that there's a lot of parallels the storage community probably doesn't see to tiling. How do you actually lay out the data in many storage devices? Can you say maybe something about that? Looking at persistent storage?
I've not actually thought more than 2 minutes about any sort of persistent storage in many years. So, but you're right. So in storage systems, somebody's optimizing the data layout and data order, and for performance reasons, it's harder to do that it's really hard to do that automatically in a compiler. There have been a couple of stunt mode success cases with the spec benchmarks, for instance, because the spec benchmarks have an outlandishly high impact on the sale of systems. Compiler writers will do outlandishly ridiculous optimizations that will only apply to this one benchmark and will never be used again. And when that spec benchmark gets replaced, that code goes away. So, like the array of struct destructive arrays optimization, which I am sorry to admit I did in our compiler back in the early 2000s. So things like that can be done, but it's global. You have a global impact, right? You're passing things to routines. Routines, the contract from the caller to the callee is the ABI. The ABI includes the data layout. So if you're breaking that contract, you have to somehow carry that all the way through the call chain. And a lot of these routines you don't have visible because you all use, well, we should be using libraries. And so how do you recompile those libraries? It's a much, much harder problem. It's great for research. It's certainly not ready with today's languages for production use in the world that I'm in today. But that's a great question. It probably didn't answer your question, but it's okay.
No. It was. I think there is like a lot of work going on right now in the storage, systems community to look for abstractions that describe data more completely than.
Well, if you can abstract it away and let the user worry about it, that's great. That's somehow making my life easier and making our users' life harder. So that's usually not my job, but sometimes that's what you do. The one over here?
Ronan Kerial from Xilinx. Several years ago, you wrote a column in Communication of the ACM about how you hate thank you slides.
I was wondering if anybody was going to bring this one up.
Conclusion slide.
So let me give the history for those of you who don't read the Communications of the ACM. So they have a column called Code Vicious. And people send in questions and he writes his answers. And one of them was, I'm giving a presentation somewhere and how do I do this and what do I put on there? And so he was giving advice about how to give a presentation. And most of the things he said I disagreed with mildly, but his last comment was, I always end with a thank you slide. That is unforgivable. For all you young people, you should never have a thank you slide. And the reason is, most of the time, the slide before this, you're spending 20 or 25 minutes giving a presentation. Your problem, your experiments, your solution, comparison, other results, future directions, and the last useful slide is the summary of your talk, the takeaway message, what you want people to remember. Now you're going to answer questions. Now all these slides are up there for about 30 to 60 seconds. Now you're going to answer questions. 5 minutes. You're going to answer questions for 5 minutes. There's the most useful slide in your talk. There's your audience looking at the slide, and you take it away and put up, thank you. Is that the most stupid thing in the world to do? So I complain about this vociferously. One person said, well, I put the thank you slide up there so people know when to applaud. So they weren't paying attention? Well, they're probably not. Now in this case, that is a takeaway message. That's all I really had to say was thank you for the award and thank you for coming. So I followed my own instructions.
Yeah. And we do have a couple of other, but I think they're pretty good questions. Are today's programming models sufficient for bringing tiling to the masses, or do we need something else to help the compiler out?
Well, we need something better than C++ or C pointers. Higher level languages, things like MATLAB. Why can't we do tiling in MATLAB? Maybe it already is doing tiling. Maybe they don't call it tiling because they came up with their own name, but I don't know the answer to that. But no, we don't need new abstractions. Now, for all of you in this, I have a lot of opinions. I've collected a lot of opinions over the past 40-odd years of being in this business. And one of my opinions is, why are we here at this conference? There's only one reason. It's for performance. We're here because we want high performance. You say, well, I want productivity. Okay, how much performance are you willing to give up to get how much productivity? You don't get high performance or high productivity by slowing down your code faster than you speed up the programmer. So we're interested in performance. If you're not, you don't belong here. If you're here, you're interested in performance, so you need to be paying attention to performance. So things like when compilers can give you feedback about how your program is running, or when you're running a program, you need to be looking at things like profiles, looking at the execution performance that you're getting to see whether you can do better. Let me give you another example, and this is a nasty comment. So I was at a workshop where someone from the NERSC was talking about how they went through code optimization for Manycore, because they have this new Cori Knights Landing system, and they had to modernize the code, which mostly means being optimized for long vectors. You could no longer ignore the SIMD operations because the cores aren't that fast. You have a lot of cores. You want to use the longer vectors to get the performance. You really need that for the performance. So they went through a long process with many of their users to optimize the code for Knights Landing, and they got the performance that they wanted, and they took the same program and ran that on the old Edison Ivy Bridge, and it ran twice as fast on Ivy Bridge as it used to run. And my comment says, it sounded like that was code modernization for Ivy Bridge 5 years too late. It happens to work really well on Knights Landing. If you had done that 5 years ago, you could have gotten twice as much science done on the old machine. It didn't happen because nobody cared. Nobody cared enough. They were getting their allocation of time. If the program wasn't fast enough, they got an allocation of bigger time, instead of saying, fix your stupid program. So things like tiling. I'm in lecture mode now. I should step down.
That's okay.
So things like tiling is part of that mix. When you're looking at optimizations, you want to look at what the compiler can do automatically, what you need to do implicitly or explicitly to get all the performance that you can. Now, that's enough about that.
Okay.
I'll stop there.
And I think we have one more question, which is, do you feel that your contributions were more visible from a non-academic career than they would have been if you'd stayed in academia?
Now you're asking me to evaluate my career. Well, I'll evaluate my academic career. So I thought I would be a natural academic because I like teaching. I'd done some teaching. I liked that. I thought I could do a good job at research. But there's 3 things that evaluate an academic, in the US anyway, is how good are you a teacher? And I was an okay teacher. I wasn't an outstanding teacher, but I was good enough. And the research I did, at the time I thought it was pretty good. Today I look at the research I did, and it's really no better than what anyone else is doing. But the third one is, can you get funding? And a lot of this is driven by the quality of students that you get. If you get really smart students, all the other things are much easier, or at least the research and the funding is much easier. So I was in Oregon. And Oregon Graduate Institute was in Oregon, and apologies to anybody here from any other University of Oregon, but OGI could get the best students in Oregon. It was a high-quality institution, had a wide range of topics. We could get the best students that are in or wanted to be in Oregon. But Oregon's not a very big state. So the really good students were going to go to a really good school. So we didn't get, and again, apologies to the graduate students from OGI, like Professor David Hansen. I mean, we had good students. We had a lot of good students, but all schools have a lot of good students. We didn't have a plethora of really excellent students. And there's a skill set to getting funding, and I did not have that skill set. So I was doomed to failure from the beginning. And sure enough, I did. So I would say, had I stayed at an academic, I would probably be at some small private school with going to this consortium of computing science colleges, talking about how to teach something, and nobody would know what I was doing. So take from that what you will.
Good. Well, thank you.
All right, thanks again for coming and staying to the bitter end.
Good.
Enjoy the rest of the week.
Thank you.